Ladies and gentlemen, we would like to continue with the last block of the UCM, which is going to be started with the Scientific 2 presentation by WIVERN, and I think Mariam is starting this. Thank you.
Okay, welcome back. Just before the break, my colleagues from the technical team showed us how they measure the main features of WIVERN mission. They are brightness temperature, reflectivity, and line of sight Doppler velocity, which are WIVERN's level 1 data products. Also, before the break, Pavlos showed us the level 2 data products. And with this slide, I am going to show you how level 1 data products are linked to level 2 data products. So I start with line of sight Doppler velocity, which is a fundamental feature to retrieve wind products. And this is a unique contribution for the mission because it's going to be for the first time using Doppler from space for retrieving wind products. Then reflectivity and brightness temperature. These are the fundamental features for retrieving clouds and precipitation products. And again, the unique contribution for the mission is the co-located use of these features for retrieving these data. It's going to be for the first time. And the same, these two features are going to be used for the first time for retrieving sea ice and snow cover data products. And finally, the use of line of sight Doppler velocity and reflectivity for retrieving ocean products. As explained also in Science Part 1, this would be for the first time enabling us to retrieve ocean products directly. I would like to emphasize that all of these level 1 and level 2 data products were fully simulated, and their performances were assessed using the WIVERN end-to-end simulator, which is called SWEEPS, except for the level 2 data products, which was out of the scope during phase A. The simulations were done using synthetic scenes and for a wide range of clouds and storm systems. Some of them are listed here. For example, we did the full end-to-end simulator for a winter storm in the North Sea. We also did the simulation for the frontal system in the Southern Ocean and also for the Hurricane Milton. The plots that are visible here are level 1 data products, reflectivity, line of sight Doppler velocity, and brightness temperature. But Alessandro, in his slides, will show the other data products simulated for the Hurricane Milton case studies. So also the performance has been validated using field campaigns. We had several field campaigns in the past couple of years. And these are the key messages we wanted to say about the campaigns and the results. First of all, for line of sight Doppler velocity, we implemented the polarization diversity pulse pair, the PDPP, both on the ground and on an airborne platform. And the red curve and blue curves shows the results of the retrieved data product. And we also flew through different weather conditions that it made us confident that actually the system works for retrieving high wind speed, such as those we get in a hurricane. We also implemented the radar radiometer mode for retrieving brightness temperature and reflectivity, as I just said, which is fundamental for retrieving clouds and precipitation products and the sea ice and snow. We are confident that these technical features are perfectly working and are able to retrieve the key measurements for the WIVERN mission. I stop here and I hand over to Alessandro, who can tell us more about these data products and how they are used to address science. Thank you.
So good afternoon. So what I will try to do is to use end-to-end simulation to showcase level 1 and level 2 products, so to show you what we measure and what we retrieve. And to do so, I will use the most iconic of storms, which is hurricanes. And in fact, I will use Milton hurricane. We have simulated Milton hurricane when it was in the mid of the Gulf of Mexico, during 2024, October 2024, and was a Category 5 hurricane. So just to show how powerful is WIVERN, it will take a shorter time than it will take to play actually this video. Okay. Okay. So what you can see here is the output of this storm resolving model, and what you see is the three-dimensional structure of the hurricane. You can see that the eye wall, the spirals. You can see the anvil coming out from the eye wall and towering the hurricane. And to show better the vertical structure, what we show is the total water content, and we use different cross-section, horizontal cross-section, and we leave the total water path in kilograms per square meter as a background image. And now, WIVERN is coming, and in a descending orbit, passing east of the hurricane high and making the full three-dimensional scan. You see that we have a 800 kilometer swath, and we have 40 full rotation. You can see the full three-dimensional structure, and this is actually our level 1. So it's the reflectivity, which is essentially backscattered power. Now, how we use this backscattered power? We transform the radar reflectivity above the freezing level. We convert in mass, in ice water content. And now you see the structure of the mass. It's so important to understand the anvil feedback, for instance. And you see the three-dimensional structure. You see the skeleton of the storm. And these are, of course, paramount features to understand how the hurricane engine works. Now, to understand better how it works, we need to unveil the internal circulation. And these are the model velocities. Again, we see the vertical structure. We go from the upper troposphere, and we go down, and you can clearly see, of course, the cyclonic circulation with maximum velocity up to 50 meters per second. We leave it as a reference. And now, again, here, WIVERN comes in the descending orbit with this 800 kilometers worth sampling. Now, this is the line of sight velocity. This is the dynamics. We see the dynamics of the hurricane. We see how things are moving around in the hurricane. And specifically, look at this. I mean, we have plus minus 40 meters per second, which is enough. I mean, this Nyquist that Paulos explained, is enough to capture the dynamics in the hurricane. Look at the dipole structure around the eye, typical dipole structure that you see in images from cyclonic circulation. And now, of course, again, we go from these measurements to the horizontal line of sight. This is a very straightforward conversion because it's just trigonometry. And of course, the only point is that we get the horizontal line of sight only in the stratiform region of the hurricane. I think I'm always quite impressed to see this, how WIVERN will capture, will bridge between kilometer scale to the mesoscale and to synoptic scale. This was a kind of qualitative things. Now I'll try to be a little bit more quantitative, and specifically you may ask yourself how good are the velocity, and particularly the horizontal line of sight velocity, which are our flagship product. So the error budget is straightforward because the measurements and the retrieval, the level 1 and the level 2, are connected by this mathematical relation, which is basically driven by trigonometry. The only thing we have to subtract the terminal velocity of the hydrometer, but we know very well from climatology. So we can actually analyze in detail the systematic and the random errors. And we know from the technical team, from the industrial studies, but also from experience that we have gained this year from the healthcare Doppler radar calibration, that essentially we can calibrate very well the radar using the surface as a reference, the fact that the surface is standing. And this, we can solidly confirm that the HLOS wind, the uncertainty will be less than a meter per second for both consortia, and this is a very important requirement for data assimilation. Random error, on the other hand, that includes both geophysical and both non-geophysical that has been discussed by previously, and geophysical contribution involving, for instance, inhomogeneity of the backscattering volume. But as you can see, this remains lower than 2.6 kilometers. So as a summary of performance of this product, which is very, very important, is that at 20 kilometer integration, for the reference reflectivity that we have, the bias is less than a meter per second, the accuracy is better than 2.7 meters per second. Just remember that actually the actual performance is the black curve, so we will perform much better at ISNR. Now, what I want to do now is to show you how we go from this level 2 products to do science, okay? And of course, there is typically some of these products serve only a specific goal, like for the secondary product. On the other hand, for other products, like the winds, for instance, the dynamics, they have an impact in different science teams. And Mary will talk about NWP and system models later. Again, the first thing I try to do is to discuss about understanding storms. So to understand storm, you need a storm-centric approach. And of course, if you look at this image, geostationary images and measurements are perfect for following the storm evolution. So what is the added value of WIVERN? Is of course, we are not looking simply at the skin. We are looking at the body. We are looking inside the storms. And let's have a look again. Let's use again Hurricane Milton as a test bed. So Milton actually took 5 days, yes, to go from tropical storms to category 5 and then make landfall in Florida. You can see the full evolution move in the GOES infrared images. And I pause the video every time there is a WIVERN overpass in the area, showing the WIVERN samples acquisition. Out of 10 overpasses in the Gulf of Mexico, 5 have ground track within 400 kilometers from the ice. So this means they will be within our swath, will be very good to provide the full structure of the hurricane. Now, I want to draw your attention to 2 specific overpasses, number 2 and number 3, descending, separated only by 24 hours. And they are across the rapid intensification period of the hurricane. You see that hurricane is passing from category 1 to category 5 within 24 hours. This is something we still do not understand. So I will now exploit our end-to-end simulation to demonstrate what we can actually do quantitatively with WIVERN. So in fact, we have seen this measuring things from different looks. Forward and backward scans. So what we can do is can put together this very difficult to interpret line of sight velocity and build the vector, the horizontal vector wind. Let's take a look at the result for category 1, for the category 1 overpass. So what we have is the reconstruction of the horizontal wind. So what you see on the left-hand side is the WIVERN reflectivity, in the center WIVERN reconstructed wind, and on the right-hand side the reference wind from the model. And what we do now, you see, we go from lower levels to upper levels. We do the full scanning, okay, stacking of things. And you see that we go from the cyclonic circulation, and then we see that as we go up, we see the upper level divergence. Okay. Okay. Of course, this upper level divergence is what is the result of the parent convection, the training ice. In the upper level. So the link between convection and anvil, very important. Now, what does this example demonstrate? That I think demonstrate clearly that we can provide a unique and unparalleled reconstruction of the vertical wind structure, features like vertical wind shear, upper level divergence, and heavy circulation will be fully captured by our sensor. Now, think about repeating. Now, remember that we have 2 overpasses within 24 hours. So we can repeat the same exercise for the second overpass, just 24 hours later. Okay, after Milton has undergone the rapid intensification period, that became category 5. So if we contrast now the 2, up is category 1, bottom is category 5, we see clearly the intensification. We capture the intensification. By the way, you see that we retrieve winds where we have reflectivities. Okay, only where we have reflectivity in cloud is an in-cloud wind mission. Okay, and then we see that as you go up, okay, you can see that of course the category 1 was less intense, but also you see the structure in the upper level. We see a change in the anvil outflow direction, moving from northward to southward. 2 major take-home messages here. The first one is that Wyvern will map the change in the internal storm. So you see, I demonstrated that we map this change and this rapid intensification. So we look really at the metabolism of the storm. And the second thing is that, in general, we will have closing time overpasses of long-lived storms. Hurricanes, they can live 2 weeks. There are mid-latitude storms also they can live longly. So this will provide a unique insight in the physical processes that underpin storm evolution, like rapid intensification. Now, passing to another example, pathway to science. Our theme, constraining cloud and precipitation feedbacks on climate, I do a little bit on polar snowfall. I mean, before, has been shown by Kati, this plot, actually on the right-hand side, but basically it's part of a very recent paper where you see a recovery. You see after 2021, there is a recovery in the ice over Antarctica. And this is attributed to some increase in precipitation, particularly in East Antarctica and in the Antarctica Peninsula. So clearly this highlights the need to monitor changes in snowfall and precipitation, but where? At regional and seasonal scales, in this case in high latitude areas. In order to do what? In order to study the ice mass balance in glacier basins. So what is the current roadblock in current observing system? Well, if we think of nadir-looking radars like EarthCare and CloudSat, definitely is poor sampling. Okay, so you can actually see here, visually on the left, you see the benefit of Wyvern versus a nadir-looking radar, the blue versus the red, for a single overpass. Now, when we cumulate orbits, the plot on the right shows the outstanding advantage in sampling, the famous 70 times effect, that comes from cloud. So now, is this mirror, this benefit in sampling, is this mirror in a much better cloud and precipitation seasonal climatology? Is this true? Well, let's take the peninsula again. Let's focus on the peninsula, and which is characterized by strong spatial variability in snowfall. We use ERA5 as a reference, and we move across from 2011 to 2020. And the bottom plots, they compare how Wyvern and how a nadir-looking radar will sample actually 3-month period snowfall at 0.25 degrees. And I think this clearly demonstrates, I mean, the total random error, normalized random mean square error is that one. So that Wyvern will be actually our gauge in space to monitor changes in snowfall precipitation at regional and seasonal scales across regions that are very important for this, like, of course, Antarctica and Greenland. And now, Mary Borderies from Meteo France will talk about the benefit for numerical weather prediction as a system model.
Thank you. Hi, thank you, Alessandro. So it's my pleasure to now show you the potential of Wyvern for improving numerical weather prediction and Earth system models, which is the last primary objective of Wyvern. Within this last primary objective, we have different science objectives. The first one is to improve NWP model forecast through data assimilation. The second one is to improve future AI-based model. And the last one is to improve Earth system model. Wyvern will provide many observations that will be useful for these 3 science objectives. First, it will provide reflectivities to infer information on the cloudy and precipitating variables. It will also provide wind variables to provide insight on the dynamics of the system. Here, I will mainly focus on the horizontal wind provided by Wyvern. And in particular, I will show you that Wyvern horizontal wind observation could improve NWP model forecast. So the first step when we want to assess the impact of a new observing system is to simulate this observation. Here I'm showing you an example of a map of Wyvern horizontal line of sight wind observation simulated from the operational NWP model page of Météo France. And you have to imagine that this kind of map will be available every 600 meters in the vertical as long as there will be clouds. So to assess the impact of a new observing system, we can use 2 different approaches. We employ both, and I will start by describing the impact of Wyvern using an observing system simulation experiment. I will not detail the OC framework, but we use the OC framework that was developed and validated at Météo France for the last few years, and it is described in Rivoire et al. So here we are using the global operational NWP model of Météo France, ARPEG, and we made the experiment for a 6-month period. On the y-axis, you can see the pressure level, and on the x-axis, you can see the forecast range. And what I'm showing here on the color bar is the impact of WIVERN when we assimilate WIVERN on top of the 2030 foreseen observing system. Negative values indicate that WIVERN has been able to reduce the variability toward the reality, meaning a positive impact of WIVERN. And here we see a very beneficial impact of WIVERN through the entire troposphere. This is for the northern hemisphere, but this beneficial impact is worldwide, as you can see here. WIVERN wind observation will not only improve the winds, but it will also improve other variables, for instance, temperature, which are shown on the bottom panel here, and we can see a large beneficial impact in worldwide, but more importantly in the mid-latitudes. We also obtain similar results on other key variables, such as, for instance, humidity and precipitation. And improving the precipitation is very important, for instance, to make progress in terms of flood forecasting. We obtain similar results than the impact of, for instance, of a constellation of 6 satellites. So our large impact is very comparable to the impact that we can obtain with other observing systems. Now, here I demonstrated that WIVERN could reduce forecast error. How does it translate, for instance, in gain in lead time? What is the gain in lead time? It's a measure by how much in advance your forecast will become more accurate with WIVERN when it is assimilated on top of the baseline observing system. So here on the y-axis, you will see the gain in time as a function of the forecast range on the x-axis. And we will show you the gain in lead time for the key variables that are usually used by the forecaster to make weather forecasts. But before showing you the impact of WIVERN, let's put a bit of context. For instance, Météo France strategy aims to achieve a 1 to 2 hours improvement in the lead time prediction of extreme events. This means that they want to have, the aim is to gain a 1 hour extra warning time to alert people, for instance. And to make this happen, Météo France plans to do improvement across all the different components of the NWP system. So now, how does it compare, for instance, with WIVERN? When we assimilate WIVERN, we gain a 45 minutes to 1 hour improvement, which is almost half of the gain in time that we want to achieve, which is quite impressive given that the fact that this lead time improvement is coming from the addition of only a new satellite observing type. So this improvement has been calculated at a global scale when we account for all the different meteorological situations, but it is expected to be larger, for instance, on extreme events. And talking about extreme events, we also could assess the impact of WIVERN to improve the prediction of extreme events, and in this case, it is shown for Mediterranean cyclone Ianos, which happened in 2020. On the left panel, you can see an ensemble of trajectories that were predicted by the WRF model when WIVERN was not assimilated, but only the baseline observing system was assimilated. When we assimilate WIVERN, we can see that the spread of the different trajectories has been reduced, meaning that the assimilation of WIVERN has been able to reduce the uncertainty in terms of the trajectory before the Medicane would hit Greece. So, as I said before, we also assess the impact of WIVERN using the other impact assessment approach that can be used to assess the impact of a future type of observation. It is the ensemble of data assimilation approach of ECMWF that has been used for the last 20 years to assess the impact of new observing system. And here we use the global EDA system of Météo France. In this method, we can assess the impact in the short range by assessing the ability of the new observing system to reduce short-range forecast uncertainties. And as you can see here, the impact of WIVERN is significant and very positive through the entire troposphere. Now, how does it compare with the assimilation of other wind observing systems? Let's have a look with Aeolus 2, for instance. So Aeolus 2, in violet, will improve the upper troposphere as well as the stratosphere, whereas WIVERN will have a larger impact in the lower troposphere. And in the mid-troposphere, we can see that both observing systems have a similar impact. But when we assimilate both observations jointly, we keep decreasing the forecast uncertainties, and this is only driven by the unique nature of both observing systems. EE11 will provide clear air wind observation as well as observation in the very thin cloud, whereas WIVERN will penetrate through the cloud and provide in-cloud wind observation. And this complementarity in terms of observation coverage, here we demonstrated that it also translated to complementarity in terms of forecast improvement. Here it is shown for EE11, but we also demonstrated a similar synergy from the winds that were retrieved from infrared and visible observation. So we assess the impact of WIVERN using the two methods that can be used. But I just want to point out that this impact is probably underestimated because WIVERN will also improve low-level humidity fields with the brightness temperature. It will not only improve the troposphere, but it will also improve the representation of surface current as well as CS concentration at the interfaces. And it will yield to an improvement of different components of the Earth system models. And it will also be able to initialize cloudy variables. For instance, here, ECMWF has shown you that the assimilation of CPR reflectivity observation could improve short-range wind forecast. With WIVERN, we will have 30 times more observation. And this larger number of reflectivity observation will not only be beneficial to provide a more accurate representation of the initial state, but also to improve the representation of the physics within the future Earth system and NWP model that will be running at a kilometer scale resolution in 10 years. And as you can see here, WIVERN on the left panel shows the distribution of the cloudy variable as a function of the altitude within the atmosphere for a selected region over the Pacific Ocean in which there are still some large biases in Earth system model. We compare this climatology with the one observed by CloudSat in the middle panel. And we can see that we see departures from the one-to-one match distribution. And however, with WIVERN, we have a better representation of the climatology. And this is due to the unique sampling capability of WIVERN that can provide in just 1 week the number of samples that CloudSat or EarthScale would take a year to collect. And with that, I will pass over to Mariam.
So far, we have showed you the impact of WIVERN's different data products and how they can address different sciences. We would like to highlight that based on these results, we have built a network of the user communities already interested in the WIVERN data. So I don't go through them, I have already been notified. So I just say that, for example, these are lead scientists in the field. Sandrine Bonny said that by providing an unprecedented opportunity to reveal the internal structure of clouds, including the mesoscale circulation within clouds, the WIVERN mission will fill a fundamental gap in our knowledge of cloud dynamics. We also have the statement from AWI Thomas Young, who says that perhaps the most impactful feature of the WIVERN mission is the provision of data over polar regions for the polar precipitation. We also received letters of support from the major Met services across Europe, and they all collectively saying that they are interested in the WIVERN data, as they expect WIVERN significantly improved forecastings. We also received letters of support from IFRIMER, who is the Global Institute for Oceanography, and they are saying that they are really interested in WIVERN's ocean data products. So we serve different science communities from atmosphere and ocean and cryosphere. So you already said in the previous science part, WIVERN is unique because it's the only mission that it provides the data inside the metabolism of the cloud system, inside the clouds engine, and all of its measurements complement the measurements of the other observing systems. I conclude with this slide. Why now? Global warming is changing storms, and we have a low level of confidence about these changes. WIVERN provides insight into these changes in response to the climate. Global storm resolving models, such as Destiny, run at kilometer scale, but they need matching global storm resolving observations. AI-based forecasting show promise, but their performance depends on the availability of dense and high-quality data. and that is, could be provided by WIVERN. WIVERN provides large volumes of high-resolution winds, clouds, and precipitation across the scales, which perfectly satisfies these data-hungry models. And finally, it's already late. The need for global storm dynamics observation is urgent. Thank you.
I should have come earlier. It's really nice to get all of this applause. No, again, we have heard, as before for CAIRT, basically 1.5 hours of really excellent presentations. Again, excellent in time. We were told that the only people that were really off time were the programmatic presentations. That's basically me and Bernardo, so we were the only ones that were really running late. So we will try to do better. Of course, we all would like to focus on the scientific aspects and the technology itself, but the programmatics are important as well for us to see that all of the missions are fit to go forward into the next phase. So I will be doing again the scientific maturity, and Bernardo will focus on the technical one. This might seem like the most boring slide, and it probably is the most boring slide of the whole day. However, it's important because with this one, we also ensure that the scientific maturity is there. And as before, for CAIRT, also WIVERN Phase A scientific feasibility has been demonstrated in the activities, which has been documented in the report for mission selection, as well as the fantastic presentations that we've seen today. So both by the MAG, by the campaign teams and the study teams. So we have seen that they quantified, or they can quantify, the scientific performance based on the validated tools, and that there are scientifically justified test scenarios allowing a rigorous computation of uncertainties. They have also established a draft mission calibration and product validation strategy. As for CAIRT, this is also important going forward. They have demonstrated a high interest in the mission by the scientific user community. This was also just shown by Mariam with the last slides. And they also provide a first evaluation of simulated and measured data, which we also have seen with the model data and the nice animations that were just being shown. So on this basis, it is judged that the candidate mission team has successfully demonstrated mission performance and has basically assembled all of the evidence that is needed to declare that they are at the science readiness level 5, which is important to be at the stage after the Phase A, and which would then also allow them to proceed. So basically here the summary, Phase A objective to mature the mission science to proceed into the implementation has been achieved. Again, as for the CAIRT mission, we've been also asking the teams to assess critical elements and risks. And here the MAG and the campaign and the MAG campaign and study teams, they consider that the mission carries a low scientific risk. This has been based on the established level 1, level 2, and also the validation activities that are coming from operational missions, but also of the heritage missions, as it has been demonstrated this afternoon. And they also have, in particular for the level 3, a very robust scientific evidence that this will work. So here we have also this evidence which comes to us that we can consider this of a low scientific risk. Again, going forward and to mature the mission into the future, going towards the scientific readiness levels, what we call 6 and 7, so towards basically towards the launch, they've identified a number of points where they would be focusing their activities. For one, it's the refinement of the level 2 products, the vertical wind retrievals, the novel radiometer mode for clouds and precipitation, and the integration of artificial intelligence techniques, and what we just said before, also the level 3 product developments. Also, one important element to be pursued further is the development of a fast simulator for Earth system model integration and improvement. This is something which has begun, but this is something which they have to focus for going forward. Then exploring the impact of assimilating WIVERN products into global forecasts and AI-driven models. That's also something which we already have shown that, or the team has already shown that they're on it. Refining the retrievals for the new objectives, sea ice and snow, as well as for ocean surface winds and currents. And then finally, exploring the impact of assimilating wind and ocean data products on air-sea interaction and coupling. So this is the way forward that the CAIRT team, that the WIVERN team has been providing to us to ensure that we go forward well. It's the second time, I'm sorry. I mean, the last couple of months were all about CAIRT and WIVERN, WIVERN and CAIRT, and I do mix up my children as well from time to time, so don't worry. And with this, I hand over to Bernardo.
Thank you, Torsten. Well, it's my pleasure to provide to you the last presentation of this afternoon and also the last presentation of today, which is a summary of the programmatics for the WIVERN mission. This morning, first I would like to provide you an overview of the key achievements on the phase A for WIVERN, which are basically the same ones as this morning for CAIRT. The first one, the system studies and the whole phase A preparation activities. I've defined, as you've seen in the technical presentation, a technically feasible system concept which have the capability to fulfill WIVERN mission objectives. The phase A has also identified items requiring technology pre-developments, either due to their technological maturity or because of the relevance of the technical and programmatic feasibility for the mission. And in addition, it has also identified, as this morning, requirements that will require also close attention during the mission implementation. With these two elements, as well as CAIRT this morning, WIVERN has initiated technology pre-developments to mitigate risk and progress to TRL5, and as well, it has established a thorough and structured development plan, which is aligned with the phase B2 CD E1 development strategy in order to achieve TRL5 at the end of phase E1. Therefore, it can be concluded that the phase A objective to mature the mission concept to proceed into implementation has been achieved. Similar as this morning, the following slides show a summary of the technical maturity, critical areas, and risk, and starting with the payload, the high-power amplifier assembly, HPA, including the AIK, the extending interaction cluster, and the electronic power conditioning. The Faraday switches, the quasi-optic network, and to less extent the antenna reflector are considered critical items for the mission. However, it is important to mention that these items have also an extensive heritage from, for instance, EarthCare in terms of the HPA, and also for electronics on the Poseidon 5 for altimeters or developments on Roselle. And of course, as it was mentioned this morning, for the scan mechanism, which is a reuse of CMR. For the satellite, excuse me, and the platform, WIVERN platforms are based on ongoing developments within the Copernicus Sentinel and expansion mission, of course, with the necessary adaptations to accommodate, in this particular case, the antenna, the payload module, and of course, the fulfillment of the mission performance. These adaptations do not introduce any specific risks in terms of feasibility, platform capabilities of heritage. At system level, in terms of items, performance, requirements, or system level elements, as it was highlighted during the technical presentation, the mission point in performance is a critical and very important element that drives, for instance, the need of a gyroscope and reaction wheels, and it has been clearly highlighted as well in the presentation. The scan mechanism is also an item that requires close attention because it is an essential element. But I have to say again, it was mentioned clearly in the technical presentation that it is foreseen to reuse the CMR mechanism with minimum adaptations. Finally, the integration and mechanical balancing of the payload within the platform and the subsequent plan for accommodation with the launch. WIVERN is compatible with Vega C launch mask capabilities, and as it was stated as well in the technical presentation, uses all the Vega C available envelope. There is some margins in terms of the GNSR performance, which is translated into about 50 centimeters diameter margin in the antenna that will allow the potential adjustments of the satellite or payload design, or also the balancing. During the phase A, pre-developments on the critical items that I've mentioned before has been initiated, as you've seen during the technical presentation. And of course, during the phase A1, these pre-developments will continue to be on our focus. Particularly developments on the high power amplifier, and as well on the Farad switches, which several suppliers has been put a lot of attention during the phase A. Expanding a little bit more into the overall phase A pre-development plan for the whole payload. You can see here a block diagram of the payload that it's also you've seen in the technical presentation, and in orange you can see the critical items and the pre-development initiated already in the phase A, the high power amplifiers, the switch matrix, the quasi-optical networks, for instance. In yellow, non-critical items that has been initiated in phase A and will also be continued in the phase A1 to increase the TRL and retire risk. For instance, the high power calibration coupler or the low noise amplifier will continue. And in green, mature items not requiring pre-development during the phase B1, which is basically the digital backend, as it was mentioned. So the results of phase A pre-developments and the proposed phase B1 technology pre-development plan are considering suitable to retire the identified risk, confirm performance, and reach the target TRL 5 at the end of phase B1 on critical elements. For the development approach, WIVER will follow the same phase development, phase B1, B2, CD, E1. And both consortia have proposed a parallel development, meaning parallel development on the instrument, on the platform, and at satellite level. At platform and satellite, it follows overall a typical satellite protoflight model approach that will be used for thermomechanical electromagnetic compatibility at satellite level. And for payload, there will be structural models and engineering models of the payload assembly in different forms and ways depending on the consortia, and also engineering models and engineering qualification models for critical elements or critical units. The schedule for WIVER is driven as well by the instrument development with the high power amplifier on the critical path. And assuming kickoff of the phase B2CD1 in the first quarter of 2028, the launch is expected in the 2033-2034 timeframe, including the appropriate schedule margins. WIVER also adheres to the relevant ECS standards, adheres to the use of European launchers. There are no ITU regulatory issues. You've seen also that in addition to the normal modes, there is a silent mode in order not to perturb radio astronomy radars, which is a decision that is taken, similar as in healthcare, if I'm not mistaken. And WIVER will re-enter in a controlled manner. As the same remark as I did this morning, the application of the new space debris regulation, which was not in effect at the time of the 11th call, will require additional adaptations to the satellite design and also additional analysis. In conclusion, WIVER has reached the required scientific readiness level and also the technical maturity at phase A. WIVER payload benefits from heritage on past mission and also past developments. The results and achievements of phase A pre-developments and the expected successful outcome of the planned pre-developments in phase A1 will retire the risks, confirm performance, and reach the target TRL5 on critical items by the end of phase A1. And as a result of all this, it can be concluded that WIVER is considered sufficiently mature for selection as the ESA's Earth Explorer 11. And as this morning, again, very important slide. I would like to thanks to all the teams, the MAC, the science team, industry, the campaign support, and all the companies and institutions that have been working very hard during these years in order to show to you these presentations and also all the reports that you have. It's really an amazing effort that not only WIVER but also CAIRT have done to reach here. And I would also like to thank you, especially Mark Drinkwater, who, as he said this morning, he will be retiring, and all the people of his generation who yes, who at one point in time, 20-something years ago, dared to dream and put this program ahead, for which you've seen so many amazing missions flying, and I hope many more to come. So thanks a lot to everybody for being here, also on the other side, remotely, and questions will be welcome. Thank you very much.
So we will now invite the Wyvern, Mag, and technical team on the stage. For the participants online, please use the opportunity to send in also your questions. Just to give you an outlook of what happens with the general discussion. So we decided that we will have another round of questions to the individual teams. So we are foreseeing something like 25 minutes for each. As the discussion this morning, we had to cut short a little bit. So we decided that we give each teams, again, equal opportunity. So be prepared if you have then still questions for CAIRT, for example. You can also post them. What we will do in the general discussions that we start with 25 minutes of CAIRT. Then we go back to Wyvern, as we have seen that some of the online questions came in a bit later in the case of CAIRT. So we would expect something similar for Wyvern to happen. And then we will have something like 10 minutes for more general questions. So with this, I invite questions from the floor and also from online. And I hand over to Mariam to moderate this.
Thanks a lot. So we are happy to receive your questions. There is someone, yeah. Can we have a mic here as well?
So Philippe Chambon from Météo France. So thank you very much for your very interesting presentations. I'm interested in the synergies between the radar and the radiometer. I think it will certainly be the first instrument having both capabilities. And as former co-chair of the International Precipitation Working Group, where we do use a lot transfer learning between reflectivities and brightness temperatures, I was wondering if you could elaborate a bit more on what way Wyvern could help for precipitation products.
Yes. Maybe can we go back to the slide on the field campaign, because we have as mentioned by Mariam, we have implemented this on the aircraft, so a radar radiometric mode. So maybe didn't cross. I mean, the audience, the message. We have a 94 gigahertz radiometer and radar with match beam, okay, which are looking at the same atmosphere. So this is a very nice example because it's kind of textbook. So you see in red the brightness temperature measured by the radiometer, and the color is the radar reflectivity 94. And we were flying over the field of clouds that you see on the right-hand side. And what you see in the brightness temperature is that, for instance, at the very beginning, you start seeing a flat and then you start jumping, right? So this is a classical behavior, 94 gigahertz, reacting to emission from clouds. And you see that in the first part, actually, you don't see any reaction from the reflectivity. So what's going on? You are flying over cumulus clouds, very small droplets. We don't have enough sensitivity to catch them with the radar. But the radiometer is perfect. As soon as you see some liquid water path, boom, reacts. Immediately emission, immediately reaction of the brightness temperature, right? So that the radiometer you see is covering the cloud bit. As soon as you start having cumulus producing precipitation, so like at 1427, all of a sudden you have reflectivity, boom, you see the signal in the reflectivity. So the synergy is very, very powerful for retrieving. I mean, we are talking about, another thing I have to say is, of course, we are talking about 94 gigas. We know that we cannot retrieve very high rainfall. Okay, when there is very high rainfall, of course, attenuation starts kicking in, and of course, at a certain point, we will lose the signal. But for this kind of clouds, cumulus, stratocumulus, producing precipitation, this will be a perfect system. Now, what is the uniqueness? The uniqueness is that the footprint is sub-kilometer. Now, if you think about these fields, right, you see that the structure is sub-kilometer structure. So you really need to capture the sub-kilometer structure with a sub-kilometer footprint. Now, what is the benefit for the constellation of passive microwave? I mean, when I started working, I remember back in the days, well, I mean, Chris Kumarov, the problem was non-uniform beam filling from the passive microwave radiometer. They have very large beam width. So this means that, think about it, right? So if you have a footprint of 5 by 5 or 10 by 10 kilometer, and you have a tiny stuff that is just filling in 1%, 10% of the signal, you basically don't see the signal. Okay? But what we will have, of course, what we have is if you go back to, can we go back also to the first part, where we have the scan, where we show actually the feature that Pavlos was pinpointing at. So the feature that we see at the edge of the scan, we have practically not almost complete coverage. So WIVERN will provide for the first time, okay, because we have done a lot of this training using, for instance, CLOUDSAT with the passive microradiometer. What is the problem there? That you have CLOUDSAT, which is a curtain, a line, and you have the passive microradiometer. So you can try to train that, but you're not feeling the footprint. So in fact, many scientists have advocated for having a cloud radar with at least 10-kilometer footprint. The 10-kilometer footprint is to have at least to cover the footprint of the radiometer. So if you go to the, we have, I mean,
Yeah, it's okay.
no, I wanted just to show that in the edge, we really feel the swath, and this would be a perfect system for training passive microwave radiometers. Of course, we have a lot of intersection. Maybe.
I hope that answered your question. Any more questions?
Yeah, we can go. Should we go for the online question? Can I grab that mic and maybe if you use the mic from... I thought, actually, can we start with Graham Stevens?
Yeah, we can start with that.
So, let me just find it. Yeah, so we got an email from Graham Stevens early this morning. He is the Director of Climate Science at JPL NASA, and he makes a little statement, but I think it's really important actually for the audience to hear this. It's under the leadership of the WCRP DUX Core project, hundreds of scientists worldwide have come together to prioritize the role of convection in climate change science. This growing international initiative, known as the Decade of Convection, encompasses significant advancements, et cetera, et cetera. However, this momentum is currently at risk due to proposed budget cuts from NASA, which I'm sure you're all aware of. You know, the beautiful big budget has just been approved. 55% cut in NASA Earth Sciences is planned, which threaten the continued operation of legacy missions, terminate ongoing programs, and cancel future initiatives. There is a growing concern that such developments may severely hinder our ability to meaningfully progress in understanding climate change. So that's sort of almost a question for both. But he says, in light of this evolving landscape, how does the WIVERN science team plan to leverage the existing international momentum and ensure the inclusion of US scientists in this global scientific effort?
I think this is a very relevant question that also it can apply to the example of the NASA A-Train and the Earth-Care experience. NASA first flew the A-Train 20 years ago, and it took time for them to create momentum in a science team. And now in Europe, we're experiencing the same thing. In the US, they have a mature team. In Europe, we try to build that team. And I think undeniably, if the funding is in place, our US colleagues will benefit and they use the data from Earth-Care. At the same time, we're going to be developing our own team here, and hopefully a team also for WIVERN. So regarding the interest, of course, we're talking about If you look at the decadal study in 2017, clearly convection was highlighted in the decadal survey of NASA. There were a line of missions designated and prepared, even funded and selected, but as Graham says, they're in jeopardy of not happening. But the justification is still there, and Wyvern proposed to do this kind of research, and probably in a very comprehensive way. Looking at the US, the strength of the US is radar. The strength of the US is mesoscale organization. If the bulk of the measurements done in the mesoscale organization and the weather community has been done in the Southern Great Plains. So do expect them to have a great interest on that. They know radar, they know mesoscale meteorology, and they have a strong heritage from their own NASA train. I think that gives enough reasons for this crosstalk and collaboration. How this will happen is more programmatic, and those who are in the room and beyond should find a way to make the thing happen. But in terms of this is of relevant, it's absolutely relevant, not just because of the gap, because there's a strong heritage over decades of measurements in the US and with the NASA missions that really maps very well what we're projecting to do with the Wyvern mission.
There's a sort of follow-on question from another US scientist, Susan Heaver, who is a University Distinguished Professor at Colorado State University and the lead PI on the INCUS mission. So she has the same concerns about INCUS, which is now at risk despite its successful technical progress and so on. But she does have a specific question related to the fact that INCUS may not fly. And her question is to the Wyvern team, is how does the Wyvern mission intend to address the diversity of storm systems, particularly in relation to anvil convection?
Okay. So I am Remy Roca from CNRS. I'm happy to answer a question from Sue. And actually, I'm also going to put my own spin on the question of Graham, because I think he's raising extremely important points, which Pavlos already started to address. I just want to start with the fact that we have a very nice international community around deep convection and storms. It's been built in the long time for now more than 2 decades, starting with STREAM, Megatropic, CloudSat, and it bridged from the US to Japan to Europe. And now we are very happy to have the modeling people joining us from Kilometer Scale Global Model. So it's a big community. It has been very active under the GeoX that you all know, the core project from WCRP. And all of this energy, it's up to us to make it, to stand up for it now, I think. And I think we are in good shape. We've been more or less all involved in the science team from the US for over the last 20 years. We have plenty of connection. We are ready to help to be inclusive with all of the scientists from all over the world to keep doing what this bunch of hundreds of scientists have identified as a priority. So we are ready to help and to contribute. And I think Graham can get our very warm support for these very tough times. As far as Sue is concerned, I will extend my warm support to her because as a PI of INCUS, she's having a lot of hard times right now, and she's asking us a very tough question. Because all day today we have been arguing that there is a large diversity of storm. Mesoscale convective system, polar lows, some are more organized on the extratropic, some are more cyclonic. How do we deal with the diversity? So the idea that we have been coming up with is actually to use the GEO platform to identify the type of storm and to make some data fusion approach where we are going to put the Wyvern observation back into the mesoscale context obtained from the GEO, from the program of record. So by doing this, we are going to enhance the added value of the circulation information from the vertically resolved, the structure that Wyvern is going to give us, because we'll know in which type of storm we are and at which level of the life cycle we are. So this unique approach of data fusion will help to answer the question so that we are able to have to deal with the diversity and to turn this diversity into a strength to address the question raised by Kathy on the anvil cloud feedback. So that's the approach we have designed to this kind of problem.
Okay, well, we can carry on the sort of data fusion theme, if you like. We have another online question from Lu Zhao from Utrecht University. And their question is, Has there been consideration of synergy between WIVERN and upcoming missions like Crystal, Simmer, or even SWAT? SWAT probably won't be flying, but other related missions to jointly characterize sea ice and snow properties, improve retrieval algorithms via data fusion?
Who is going to take this? Christian?
I'm Christian Melsheimer, University of Bremen, polar remote sensing. So the other missions mentioned are basically pretty complementary because the uniqueness of WIVERN is to have rather high frequency for the spectrometer, for the radar, called spectrometer for us, side-looking radar, 94 gigahertz, has not been used with sea ice and snow before. So all the other radar missions are rather either like Crystal in the 20-30 gigahertz region, which is sensitive to the whole snow layer, or like Rose L in the 1 gigahertz, which basically will not see much of the snow because snow is pretty transparent there. And here we look at the top layer of the snow and we can determine rather the snow type, which is pretty unique. Nobody else, no other sensor can do this till now. So that's what our studies show till now.
We will also the synergy for all the cloud and precipitation product along the same line that we said before.
Yeah, I think there's some more questions from the floor. Yeah.
I'm sorry, my name is Ugo Cortesi from the Italian National Research Council, and I apologize because I'm still on synergy. And my question is to the MAG, or the larger community of WIVERN, because, of course, in the WIVERN context, the last word is given to assimilation system, which will be the first users of WIVERN data. In that context, I would be curious to know whether you see the assimilation capacities as a concurrent tool and competence with respect to synergistic use of data or even data fusion methodologies, or rather you have experienced or investigated possibilities of alliances between the two?
Eric, do you want to take this? So if I understood correctly, you're asking if we have explored the synergies of different data products for assimilation. Is that your question? Different.
Actually, to be more clear, I've encountered in previous works sort of attitude, especially from the experts of assimilation, in saying that there is no clue to assimilate synergistic products from multiple sensor acquisitions, because assimilation is already doing what also synergistic use of data or data fusion methods are doing. So I'm asking what is your position, if you have any time reasoned on that.
Well, we...
I know it's a difficult question, but...
Yeah, we will have synergy with other missions and between all the different systems as well, because we will have also surface currents information. We will also see, we will have a better sensitivity also to the lower level cloud for compared to other instruments. So I see that there are plenty of
So we have already shown in our slide the synergy between WIVERN's and Aeolus so you already saw the results. We also have got the synergy with the scatometers for the storm tracks. These are the synergies that we have already explored, but we also have in the roadmap that once we are selected, we can explore the synergies for the ocean products and cloud winds products to investigate the coupling for the air-sea interaction. So if that is kind of question that you have.
Okay, thank you.
And we also studied the synergy with respect with wind observed by visible and infrared sensors. So.
Oh, yeah. Thanks.
Okay, we've got some more online questions. Oh, well, we can go for, yeah, some in the room if. So what's the deal with the Accio members? Are we allowed to ask questions now? Yeah, okay, fine, okay. Go for it, Helene.
Okay, I have two questions. The first is that you explained us the value of the velocity and reflectivity for the big hurricane, and how does it work for the small storm tracks? What is the lower limit of interest for science, given the velocity lower estimate you can get, and the reflectivity the lower estimate you can get? So you explain us what you can measure, but in which case does this instrument doesn't help to solve the storms? That's my first question. And my second question would be, could you explain a little bit the surface current estimate, because you didn't explain it at all to the audience?
Well, in terms of sensitivity, we have, the two consortia, what we typically say, we have a sensitivity, they have a single pulse sensitivity around -19, -18 dBz. Very similar to healthcare, okay, as a single pulse. Now, of course, because we are scanning so rapidly, we are collecting few pulses per kilometer. So this means we are averaging less. So this means that when you look at what kind of clouds we are able to see, -23, -24 dBz, compared to, of course, healthcare that's just integrating many, is very super sensitive. So we'll miss all the clouds that goes, in terms of, you look at the image of healthcare, you will see that, we don't see the very thin cirrus, the very light stratocumulus, and so on and so forth. Okay? So that's the sensitivity. Now remember that Doppler-wise, you always get the Doppler where basically you're at the level of your single pulse sensitivity. The same thing is true healthcare. So basically, if you look at an image of healthcare and you look at the Doppler of healthcare, we will do exactly in the same region, we'll produce a Doppler product. Okay?
So may I ask a question to your neighbor? What kind of storm do you miss from your science with this mission? What are the limits?
Well, so it depends. So I think the shallow clouds are kind of difficult because the vertical velocity is too weak. So that one, I think we will kind of miss. But I think if you look at the generation of the deep convective clouds, the mesoscale convective system, the congestions, I think there is no issue. But I would really say the shallow cloud probably it.
The shallow clouds, we will have information from the radiometer. So as I show in the picture, you don't see in the reflectivity, you don't see the Doppler. Yes, we don't know the Doppler. But at least we see this pulsating brightness temperature, which is unique at this resolution.
So yeah, just to complement those discussions, I think once you enter the deep convective system, there is a diversity from small to huge one like the hurricane. But across this scale, we have a sort of a minimum. You have deep convection going on, so you have the minimum draft intensity and divergence intensity that makes that as soon as it's becoming a deep convective system, being smaller than a hurricane or growing faster or whatever, will be there with the Wyvern sensitivity. So we'll get the full family of the deep convective system, and that's where the discussion is whether we get some other system. But once it's deep, it will be seen.
Thank you.
Now, for the ocean, I think we have an expert.
So hello, and thank you for the question. I'm Louis Marier from Ifremer in Brest, and we were asked to look at the potential, to assess the potential of Wyvern for ocean current measurements. We were pretty skeptical at the beginning because it was a frequency band that had never been used, and the PDPP mode was also fairly surprising from an ocean perspective. And we have investigated this doing analytical calculations and using campaign data that have been communicated to us. And surprisingly, we found out that all lights were just green, and that we are now very enthusiastic that we can get meaningful line of sight Doppler measurements of surface currents. So I don't know if that answers your question. There are technical details into that, but we will get essentially direct Doppler measurement of surface currents that will complement what is already obtained through satellite altimetry. And the interplay between the two, plus having the air column wind above that, is really exciting. Is that?
Just can you precise how it completes what is existing? What is it adding to what is existing?
So what the products that are currently available are based on satellite altimetry. So you're using the elevation of the sea surface and using this as isobaric charts and deriving currents from that. And so deriving wind from isobaric charts is something that you can do on your sailing boat or something, but everybody knows that it is incomplete and there are phenomena you're not taking into account. So altimetry is doing this, and it's been something like we really dreamt of at Ifremer, was to obtain something or some other direct measurements that we could use to understand what processes are not accounted for by altimetry and really understand many of the things that we still don't know about the ocean surface. Is that okay? Thank you.
We've got some more online.
Okay, go ahead.
This is a tiny bit on the technical side. It's from Giulia Panagrossi, who is a senior research scientist at CNR. And there's a sort of quite long, rambling section at the beginning, which I won't read. So I'll sort of skip to the second part. Hopefully it'll be clear what the question is. However, some recent studies based on CloudSat CPR have shown that the presence of supercooled liquid water has a strong impact on W-band spaceborne radar sensitivity to snowfall in particular, mainly due to attenuation. And so they are asking, that can cause an underestimate of snow water content. Could WIVERN be exploited to correct for such attenuation and politely correct for underestimation of snowfall intensity?
Yeah, hello, this is Max Mahn, Leipzig University. And we looked into the snowfall algorithms, and the unique thing about WIVERN is that we get these brightness temperatures over the ocean, which are directly sensitive to the supercooled liquid water. So we're actually measuring the supercooled liquid water over the oceans and can use this information to actually make our estimates of surface snowfall rate better.
Okay. Can I ask my own follow-on question about snowfall?
Of course.
So devil's advocate here, okay? I mean, I'm a polar scientist, so anything to do with sort of improving estimates of polar processes is good to me. Two of you showed that plot from the Wang paper of increasing snowfall over East Antarctica. That result was obtained from what's called GFO, GRACE follow-up. NASA and ESA combined are going to spend probably over €1 billion on, well, it's NGGM and GRACE-C, two pairs, which are going to give us. So what does GRACE give you? It gives you mass redistribution, so it gives you that snowfall. So why do I need WIVERN to tell me that it snowed over East Antarctica when GFO and GRACE-C and NGGM will do the same thing?
I would say you need this because both of the missions are just looking at one part of the process, right? I mean, with WIVERN, you really get the flux, what is getting in, and with the missions you mentioned, you can measure the mass at the ground, right? And I think we really need both things to understand the whole process. I think just one of them is just not enough to get all the complete picture. To my knowledge, what is used so far is in all the ice sheet modeling is ERA5 or other reanalysis precipitation data, right? And this is just yeah, based on so many assumptions. So I think we can really go a big step ahead when we have direct measurements of snowfall. And Katie wanted to add something.
So from a modeling point of view, I need to know the snowfall. So, I mean, for prediction also of the stability of the Antarctic, I need to know how much is raining into my model so that I can validate the model and then use it. And that will come from the polar snowfall. So just having the mass balance is really hard to go back.
One more little one.
It's a long technical conversation we could have about this, but you can get snowfall out of GRACE or GRACE follow-on, but yeah, it's...
The idea is to do budget closure exercise where you have two different technology looking at the same. If they converge, then you trust both even more. I think we learned from a sea level closure so much that if we can do the same for snowfall, we'll be in the right direction.
That's a better argument, definitely.
And also, we will get it. I mean, we can do monthly statistics with 0.25 degrees resolution, and I think this is just better what the machine like GRACE can do.
Futurement Meteo France. So I have a radiative transfer question. So we haven't talked a lot about the polarimetric capability, I think, and I was wondering if this polarimetric capability will help documenting ice particle shapes and orientations as well, which are kind of critical for correctly modeling radiative transfer, even for all passive instruments, actually.
Yeah, we looked into that, and it's, of course, an exciting possibility. But it turns out the polarimetric measurements are most likely too noisy to add additional information in addition to that what we presented today. So since we have only, what was it, Alessandro, like 6 samples per kilometer, the random noise of these variables, which are very noisy in the first place, even if you measure them from the ground. Yeah, it's just too much. But that's something we will study more in the future, whether with more averaging we can squeeze something out, but I'm relatively skeptical.
Yeah, there is another problem when you move to 94 gigahertz, the polarimetric signal essentially gets lost because you start having, you are entering the non-Rayleigh regimes. So actually, if you look at the polarimetric, ZDR, for instance, you start seeing all these oscillations when you take for single particles, when you average them out, you basically kill the signal. So ZDR would be very, very small, given the fact that it's very noisy, is unusable, and the same applies to the other polarimetric variable. LDR will be useful. LDR, we will have good LDR, but a little bit. We'll give a little bit information about shapes and, for instance, melting layer.
So another question online from, I think it's Aouf Lotfi, who is at Meteo France. And their question is, WIVERN shows its capacity to describe accurately the wind profile in the atmosphere, particularly in the Southern Ocean. Well, you can debate whether that's the case or not. Obviously, if it's cloudy, it does. My question is, an ocean wave modeler, how might WIVERN improve the coupled Earth system or climate models, particularly in the Southern Ocean, where the ocean heat content is strongly dependent on wind forcing?
Again, Louis Marier from Ifremer. So there are areas, yes, on the Earth where the 10 meters wind is not well known, and the Southern Ocean is a place like that. So obviously, having WIVERN make measurements of the wind in the air column, these data being assimilated into weather prediction model gives us oceanographers, like end users, in fact, a better wind data to work on. And this will allow improvements in wave sea state predictions, and so we will have better wind to work on, and also potentially surface current measurements to better understand the air-sea coupling, especially in those regions where data are not readily available. Is that okay?
Well, the people, it was from online. People may fix that.
Yeah, that's right.
Not taking them in order here, but we have another question related to snowfall from a colleague of mine, Steph Lermit, who's at TU Delft. So he's a polar remote sensing scientist. And he just wondered what the accuracy of snowfall statistics would be because of the well-known high random errors that exist for reflectivity-based snowfall retrievals. So he's just wondering what kind of performance you might expect to get for, I guess, particularly over the ice sheets.
Yeah, I mean, snowfall retrievals based on W-band radars have been around for like a while now. So we have quite a lot of experience. And yes, random errors can be very high, like in the order of 100% or so. And even though when we get a little improvement by adding the brightness temperatures of the ocean, we of course suffer from the same problem. But really the advantage of the WIVERN mission is that due to these much greater sampling capabilities, our spatial sampling is so much better that, as said, even on a 0.25 degree resolution, on a monthly scale, these random errors of the retrieval, they will average out in a way that we can get meaningful snowfall statistics on that time scale, meaning the error, I think for monthly statistics, the random error is in the order of 20% on a monthly scale, meaning we have a lower error than the variability of the snowfall, and that's what matters.
I mean, we have a paper out, Scarsi et al. In the reference, you can Google it, and we have all the assessment. No. Sorry. Yeah, sorry. So we have established, basically, we have looked at the errors at different temporal and spatial scales for snowfall.
Any question from the audience? Any final question?
We do have a question from Alan Gear, who's at ECMWF, so a very much an interested party. And his question is, WIVERN can be seen as, it's quite a forward-looking question, can be seen as a first all-purpose active passive Doppler scanning microwave technology. What are your perspectives on WIVERN as a technological stepping stone towards an even broader all-purpose future microwave system with multiple frequencies down to 19 or even 10 gigahertz? So this is what, EE15 or 16 or something, I don't know, or whatever it is. But yeah, any thoughts on that? I guess he's thinking, in terms of perhaps operational applications, maybe.
Yeah, I think I made the point. It's a very good question. Looking forward. I made the point in my presentation when I took the ground-based operational radar, put it upside down. Whoever has been involved in deploying those in your countries, you know how difficult it is and how difficult to maintain. So the idea that you take that, you put it upside down, becomes a very wide swath, fast revisiting time. It's appealing. So WIVERN could as well, given also has some technology advancements like the polarization diversity and the radar radiometer, could be the stepping stone in evaluating the potential of this technology being operationalized. It is a possibility to be operationalized. From my perspective, I also see the WIVERN as an anchor point for building all sorts of constellations around. You can think of this kind of system scanning and creating Doppler signals and having cubesats of opportunity, creating multi-static approaches. That could be a completely different constellation, giving you all sorts of velocities and information. There's all sorts of capabilities and technologies can be integrated. I think there's both the integrating on top of the core, think of that as a core observatory, but itself, I think it's prove itself and provide the kind of measurements that we're saying it's going to provide. It would be a very appealing approach. And we know that the private sector has contemplated the idea of putting their own private networks in space, radars, for weather forecasting. So this is an interesting alternative that if WIVERN becomes a reality, it will be teasing and challenging, and maybe a way forward for us both have operationalization of that, but I think more importantly could be, as I said, one key piece of the puzzle where we can integrate all sorts of technology and sensors for a future observing city with a bit of different mentality, different philosophy, different approach. at different scales, because the kind of scales and capabilities we mentioned are really outstanding compared to the last 4 or 5 radars we have actually put in space the last 30 years.
Just to say that we, it's over? Okay. No, it was just also for Alan Gear to also mention that we also assessed the impact of the brightness temperature in an NWP context. So with WIVERN, we will have both for the first time the reflectivity as well as the brightness temperature. And I see that is very appealing for future spaceborne mission.
So thanks for the questions, also from online. So the idea of the general discussion is now that we have both teams on the podium. This is not a dance or face-off. This is just to give them visibility at the same time. We have been debating on how to best do this. We've seen that there are still some questions online as well for CAIRT. There were questions before this morning for CAIRT also on the floor. We have online questions still also waiting for WIVERN, and we would like to give the online participants more time to also send and formulate their questions. So what we propose to do at this point is that we basically bring the CAIRT team on stage. So we would need to get the stairs, the chairs. So don't run away. This is hopefully going to be quick. And then we continue with the general discussions.